going to talk about this paper that we published back in July, where we used spatial compliance data to constrain and estimate the lithium resource potential from Marcellus produced water. This is our disclaimer saying if anyone gets hurt, the federal government is not responsible. These are my helpful co-authors. We couldn't have done it without them either. So I'll take you back, big picture here. So I don't know if you all are aware, but Pittsburgh and Morgantown actually has two premier national energy laboratories. So we are the National Energy Technology Laboratory, but we're one of a host of 17 other facilities spread across the United States. And we all kind of have our own like niche specialty in domestic energy security. So we have, some that are funded by the Office of Science, or some that deal mainly with the nuclear energy. So they're like either funded by the Office of Nuclear Energy or the National Nuclear Energy Security Administration. We have environmental management, trying to clean up all of the nuclear stuff that happened, 50 years ago, developing those resources. And then specifically NETL is funded by the Office of Carbon Management and Fossil Energy. So our purview is basically anything related to fossil energy, and then, emissions and other things that are tied with that sector too. So going with that, I work within the Research Innovation Center at NETL, so we have strategic analyses and a couple other initiatives. So I am specifically R&D, and I work within the Geological and Environmental Systems Directorate. And so, we have a ton of capabilities. We usually receive samples, expose those samples to fluids, pressures, and temperatures that would be relevant at a reservoir depth or a coal formation depth. And then we characterize the results and try to, infer some meaning out of that. And, and that kind of ties in with this work because we're just trying to extend the resource, enhance recovery of the resource, or come up with some type of beneficial reuse of the waste from the resource is basically what we do. And that's occurring kind of tangential to this recent thrust of the energy transition and coming up with materials to facilitate the transition, because we have some pretty lofty goals that need to be met within the short-term and then long-term U.S. domestic energy policy requirements. And I don't know, do either of you know, is everyone in the room familiar with what a critical mineral or material is? Just maybe a show of hands, if you do know what that is. All right, just gauging how far, broad picture I should go. So the USGS publishes a national list of critical minerals. They're technically elements, but you derive them from minerals that have some type of supply chain insecurity, and they are paramount to energy production, economic development, or national security interests. And sort of taking that list of minerals and putting it into the DOE's purview, we did an analysis of importance to basically the future of the nation's energy and the supply risk. And if you look, so this is a study that we did back in I didn't do it, but the DOE did it back in 2023. And we see that, in the short term, we have dysprosium, which is it's a rare earth element. But really for long-term medium term, so within, the next 20 years or so, lithium is right up there at the top. We have a supply risk issue where most of the lithium is produced in either Chile or Australia or Argentina, and then it's shipped to China, where it's processed into battery-grade lithium, and then it's exported back to the U.S. And that's an issue because at any moment, basically our entire battery economy is tied to what is not necessarily considered a hostile foreign nations, but sometimes we don't have the friendliest relations with them, right? And they could just turn off that supply. So we need to secure these domestic supply chains so that we can end reliance on these other countries and sort of have control of our own energy future. And just to give you kind of an idea, this is, wait a minute, what happened here? Uh-oh, it's not, there we go, okay. So this is a bit of an outdated analysis, but it's the most recent one to date. So this is the International Energy Agency has done some forecasting on what demand of these minerals would be, and we're looking at mainly battery related minerals here. And you see lithium within the next 20 years. So this is by, I think at this time, this is like 2035 is what this time span is forecasting, but we need 50 times the current demand, right? 50 times the amount of lithium. And if we're gonna meet our goals for 2050, I've seen numbers upwards to 500 times current demand. So we need a lot of this stuff. We're not making it domestically, which leads me to my next slide so we have to come up with secondary and unconventional sources. Now I know like this, I prepared this presentation in August, and since then they found a mountain of lithium in an ancient dormant volcano, which would supply the nation's energy future forever. But the problem is you have to dig it up, and it's excavating a mountain. It's labor intensive. It's creates other issues because then you have to leach the spodumene, and you have all of these waste tailing piles and things like that. And so what we're trying to do at the National Energy Technology Laboratory is we're trying to see if we can extract the nation's need, if we can meet the nation's need for these critical minerals, lithium specifically, with unconventional or secondary ores. So this would be coal tailings, coal fly ash. Important and relevant to this group is produced water. So we're referring to these as secondary and unconventional resources. And produced water from shale gas development is a significant unconventional resource, is what we're. Water already daily, right? This is a report from the Groundwater Protection Council. John Vail did a bulk analysis of domestic produced water volumes, and we're making about 2.8 billion liters a day. And there's a lot of stuff in this water. We know this. There's calcium that you can make concrete aggregates out of, and there are polycyclical aromatic hydrocarbons that you can pull off, and potentially you could make like pharmaceuticals. I mean, there's just this fluid has been mining the subsurface for tens of, hundreds of millions of years, and these are just materials that are waiting to be extracted. So we're really at the forefront of being able to use this new unconventional resource. And, comparing all, domestic shale gas formations and the produced water that comes from it, we see that, there is potential for lithium in, say, the Permian, where they're making 30% of that figure up there in water a day just because they have so much water. But if we look at this graph in the lower right-hand corner, we see that. So we have total dissolved solids. I'm just going to point here. So this is total dissolved solids. So that's kind of a sum of everything that's in the water and tells you how salty it is, versus the lithium, that the Marcellus stands out as having the highest lithium than any other formation at comparable TDSs. And that's kind of important because if you're going to extract something, you want to have the most efficient feedstock to extract it from, right? Now, we don't really have enough information to know like how much the concentration of lithium that is an economical point, but I would assume, and it goes with logic, that produced waters that have more lithium are going to be more attractive than produced waters that have less lithium. And so this has, we've been working on this for nearly a decade at the lab, characterizing both the waters, characterizing the rock, using isotopes to try to tie the water to the rock. Is it stable at, you start to flow back the well, like how long does it take for the lithium signature to stabilize? And that's kind of what we're seeing. Is just a summary of some reports there on the left of that. And we noticed that for the Marcellus, after you flow back the well for, after 30 days or so, the lithium concentration is relatively stable. So then you can kind of start to make some assumptions if this is like a static, it's not a dynamic resource, it's a static resource, then you can start to kind of think about making some predictions on forecasting how much you could potentially extract from this. And that's kind of where this study came into place. So we know there's lithium, the lithium is there. We know that after a certain time that the lithium is relatively stable, so potentially we could put an estimate on the mass yield, and come up with basically an estimated ultimate recovery of lithium from a shale gas well. And kind of tied with that, we've done a lot of this work. The Marcellus is like fairly well characterized from a geochemical standpoint, at least comparative to other. There's a wealth of data available for the Marcellus because we have this lab and these partnerships. We've been able to get samples, and we've published a lot of good works. And so in doing that, we've kind of realized that no two formations are the same, and similarly, no two regions within a formation is the same, and the Marcellus is no different than that. And so, what we call that as a geologist or a geochemist, it's the words heterogeneity. So that just means that it's not all the same. And we have compositional differences from the northeast part of the state and the southwest part of the state. And if the produced water and rock makeup is different, then you can assume that there would be differences in lithium content. And we've kind of started some of that work. Like this is a paper published by a colleague, Tai Fan, back in 2016, where they looked at core from northeast and southwest part of the state. And they did some inferences, and they noticed, the lithium content of the rock is different, and the lithium content of the waters that they sampled is different. But that's just one data point. You need really to shore up the resource and really understand what this looks like as a long-term solution for lithium raw materials. You need a lot of data. And so with that, that kind of informed the initial thought and the methodology for this project. And it's fairly simple. It's like we wanted to understand if spatial variations within the Marcellus Shale impact the ultimate recovery of lithium from a Marcellus Shale well. Are there variations in lithium composition that is driving these differences in production values, if they exist? And then, what is the volume of water that these wells make? Does a well from, Susquehanna County produce the same volume of water as a well from Armstrong County or Butler County or Washington County, things like that? And to really do that, and again, we're fortunate that we've had, a ton of data collected by the Pennsylvania Department of Environmental Protection. I was an environmental scientist briefly for CEC, and we went around and filled bottles up with produced water from tanks for your 26R reports, if there are any industry people in the room. And I kind of wondered, like, where did this data go? And that was kind of another thing. So we really wouldn't have been able to do this type of meta-analysis if we didn't have a decade of chemical and production water data available. And then similar to that, we wanted to just see, like, as a whole, like, we're making a ton of water. We're making 8 billion liters of water a year out of the Marcellus or something similar. How much lithium does that actually produce if we could just like extract all of it? And so the two questions is A, what would our like net lithium export be if we were able to just like pull all of the water into a central place and extract it? And then more realistically, like what volume of lithium or mass of lithium could we produce out of one Marcellus well? And so again, to do that, we conducted decline curve analysis on the water coming out of these individual wells. So decline curve analysis, or DCA, is a way that you're just essentially assigning a mathematical model to the flux of something coming out. So it's been widely used in estimating the recovery of hydrocarbon resources, and it's one of the metrics that that bankers use to prove up a reserve. So we applied a similar methodology to produced water and lithium. And to do that, we mined 5,000 or so monthly produced water volume reports, or monthly produced water reports for 5,000 wells in the state. We chose, I can get into the details of that. But anyways, we had this decline curve analysis. We multiplied it with, or paired it with this big geochemistry data set that we had mined from the state. And then because all of this is compliance data, and there are a lot of data folk in the audience here, you know that it's like sporadic and it's not really something that you can rely on like an individual number. So we used Monte Carlo simulations so we're doing, basically we're multiplying probabilities of these volumes and these concentrations to reduce the uncertainty so that we can be more sure of our result. And then we did a similar method to calculate the lithium mass yields. And so for the produced water volumetric analysis, we used waste generator reports from 6 of the top 10 producers that extract gas in Pennsylvania. And to give you kind of an idea, the 6 that we used, they totaled, I think in 2023, it was like 48% of the total gas market. So it's a pretty good representation of what it looks like. And from these reports, we pulled produced water volumes, the date sampled, we pulled the date that the well was drilled or the spud date, and then the farm name or API or some diagnostic association. And there was also, with the well ID, then you can also relate it to a geospatial location. So I have to forget I am at a geospatial conference. I am not a GIS person. I use GIS, so please forgive some of the terrible maps I'm about to show you. So anyways, you compile all of that, and it was just all over the place. It looked like a just giant scatter plot. But if you bin everything and normalize it to the spud date, so instead of looking at just a random date plotted up on a map, you're looking at this production volume as the well has been producing, you see a trend, right? And this is an empirical decline curve that we would see. This is an exponential decline curve. And once you can do that, then you can do well by well temporal analysis or time series analysis of production from the well. And we did all of this within Python. We used the SciPy optimize curve fit function. And so you plot up the data, you have some random scatter points, and then it does some regression analysis to fit your decline curve. And if we notice, we're looking at, this is the same figure. This is just the median production versus that time from spud. We see that there's an initial volume that's produced. After you turn in the well, you flow it back for X amount of days. We wanted to make sure that we weren't capturing the flowback water because that volumetrically, it produces way more water volumetrically, but it has just a little bit of lithium in there. So really that would skew our results. So we set a filter. We didn't include any of the initial production data from the spud date to 6 months past spud. So we're really looking at a conservative estimate of the volume coming out of the well because we're probably maybe not even capturing that initial transition from flowback to produced water that happens in the first 4 months, say. And so we have this initial production, and then we have a rapid decline, and then it all kind of converges on a non-zero value. So an exponential decline is going to just go until 0, right? But this doesn't. This ends at L, which is that figure right there. And we think and we assume that, and again, having experience working in the industry, I know that at some point the economics of producing a well for gas, you have this little thing called hydrostatic pressure because all of this valuable produced water is stacking up within the well column, and so they install an artificial lift system to remove the water so that gas can flow through. And this L factor is actually the static volume of water that a well will produce after this lift is installed. So, and it's about 15,000 liters a year or so. So taking that information, we developed our decline curve model. It's pretty standard form, exponential decline with a lift factor. And then to assess the total volume that's going to be produced, so we have a curve, so we just integrate it underneath the curve over 10 years. I know Marcellus wells could last, they could go anywhere from 20 or 30 wells potentially. We haven't reached that yet, but 10 is a nice round number, so we chose that. To give you kind of an idea of what the data looked like, there was a lot of filtering we had to do. So this is the well production volume reported for this particular well. I guess I should have probably censored that, but it's all public information. So this is kind of what it looked like. So you can't really make any any estimate with confidence, right, using this data. So we, through trial and error and literally flipping through, 2,000 or 3,000, that there was this overestimate in some cases of the initial production, that decline rate parameters of greater than 6 just didn't make sense. It was a vertical line. We saw that some of them had negative lift factors because that just doesn't make sense. Why would you're not sucking water back in from the surface, right? And then we had some wells like increased the volume of water with time, which didn't make sense. So we applied some of these quality criteria to the data, and what we're left were something that I was like, okay, I could kind of work with that. It's still not perfect, right? We're still working with compliance data, but the curve fits the general trend of the production. We don't have negative curve fit values. We don't have a negative decline rate where it's increasing. We don't have straight lines or flat lines or any of that stuff. But it's still not really estimating the production from that well. Well, if you do this, 10,000 times or 4,000 times, then you can start to converge on what that median curve that we looked at before. And so that's what we did. We pulled in, we started with 4,800 wells. We pulled in the produced water volumes. We applied all of our quality criteria to the initial data set so that we weren't getting wonky curves. And then we took that final one. We did the SciPy curve fit that I had shown you before. And then we wanted to at least have the curve represent at least 50% of the data that it was trying to model. So we only included curve fits with an R-squared value of 0.5 or greater. We did an IQR threshold analysis, so interquartile rank is you're just basically dividing your data into ranks, and the outliers above that rank we would have removed. And all told, 2,500 or so wells converged on a fit. 12 of those passed our IQR threshold, 1,200 of those passed our IQR threshold analysis. And then we ended up with pretty good fits in the north for 500 or so in the northeast and 722 or so in the southwest. And so we took all of those, and basically what that yielded was just a spreadsheet of the initial production, that QI value, the decline rates, and the lift. So three values that could define the production of water from a Marcellus well, from the system. Sort of, along with that, we had chemical data. We knew that there was lithium in the Marcellus. I showed you the graph. They've been studying it for nearly a decade of lithium work characterizing it, but we didn't have a really strong spatial representation of the lithium content of the formation, and so fortunately we used having sampled and knowing the existence of the 26R residual waste reports that have to be submitted by every operator. And so this is just a map of every well pad. This is just your oil and gas map of every well pad, but in the state. So each one of those well pads had to submit one of these reports at least once. Any pad or any waste generator in the state has to characterize its waste under some standard and submit this chemical waste analysis to the Pennsylvania Department of Environmental Protection. Fortunately, Residual Waste Code 802 encompasses produced water. So every pad in the state has at least one chemical profile of produced water. Uh-oh. Where did it go? Oh, I took it out. Well, I had a list of the analytes, sorry. So fortunately, lithium has a minimum contaminant threshold, and it's a regulated constituent. So we have a lithium measurement and TDS, so total dissolved solids, so like calcium, magnesium, sodium, things like that, for nearly every well pad in the state. It's just sitting in a state server somewhere, waiting to be mined from these PDFs. So we wrote some Python scripts. It was a very laborious process. We mined 2,000 of these PDFs. We did it over COVID. And we ended up with 600 or so that were actually representative of a brine or a produced water coming from the well. And we had a lot of data gaps, and so we worked with our industry collaborators, and they helped us fill in some data gaps that we had too. So all told, so these were like some of the criteria that we applied. This is what it looks like. So we have 654 chemical reports from 553 well locations spread across the state. Because they were all spatially referenced, we were able to do some meta-regional analyses. So we basically divided the data into quartiles, or quadrants. The northeast part of the state, so we're talking like Bradford, Susquehanna County, has a higher median concentration. So that's the purple that you see here. This is just a histogram of it, of 200. I mean, we saw values up to 300 up in the northeast. And then the Southwest has a more narrowly constrained concentration of roughly 125 or 127. But importantly, like both of these regions are like in the ballpark of other lithium reserves that we have that are economically producing globally. So some of the lower lithium concentrations in the salar brines from the Atacama Desert are in the 350 to 600 range. Standard Lithium is producing lithium brine out of the Smackover Formation in southern Arkansas, and their most recent press release had a median lithium concentration of 250 milligrams per liter, and so this really has the potential to be of value, and comparably to other, as we had said, other formations, it's the highest lithium of any shale producing formation that I'm aware of in the state. Or in the country, sorry. And so putting all that together, this is my awful map. I had no idea this map was going to be as popular as it was. It was supposed to just be a sub-figure. There are no masks on the labels. My CRIG was, basically I CRIG'd the lithium compositional data, and I masked it with the Marcellus Formation. And what we see in green are places where we conducted the decline curve analysis, so the DCA. The circles are the locations of the new produced water samples that we were able to collect. And then we supplemented with data from the USGS National Produced Waters Database, which are the squares that we're seeing. And kind of what you see from this map is that, so darker colors are more lithium, lighter colors are less lithium. The northeast part of the state has kind of a bullseye of it's darker, more lithium, therefore you would think in your head that it would have a higher EUR and a higher total lithium mass yield per well. And then, I'm going to tell you how that's wrong in a little bit, but surprisingly. So similarly, we compiled all of those data points, and we used to calculate just the annual mass yield, so that big number that we've seen reported in the media. So we used 5 years of the total volume of produced water coming out of Pennsylvania, just so that we could have a distribution to work with. And so, we compiled everything. We used Monte Carlo's framework to do our analysis, so that involves creating random sample variants. So we have all this empirical data that we've collected and we modeled, but we need to really converge on the mode of the system and to reduce the uncertainty of the estimate. You can't rely on really the empirical data. As we'd seen, it's kind of all over the place and it's really noisy. And so what we did is we took that and we mapped it using what's called a probability distribution function. So we're looking at the probabilities of any value occurring. And then we created a randomized data set using the probability of those occurrences and ran production simulations. And we did 25,000 production simulations. So essentially we simulated production from 25,000 random Marcellus wells using this data. And then we took the volume of water that we had derived from that and we multiplied it by another random but probable lithium value from our lithium data set. And this is what the results are. So so the graph on your right is it's just the median water volume that's produced from a typical Marcellus well in either northeast or southwest PA, and then the quartile range. So Q2 to Q3, is what the shaded area is. And there are a couple takeaways. Northeast Pennsylvania wells have a higher range of initial production, so there's potential, to make 3 million liters a day or so initially, but it has a steeper decline, a sharper decline. And so ultimately, Southwest Pennsylvania wells, they make almost 2 times the amount of water over a comparable time scale than a well in the Northeast. And additionally, with this data, we were able to just model the decline rate of an average well. And so 80% of the water that's made in most of these scenarios is within the first 2 years. And then you start to transition to that harmonic or that lift factor, so the static production of about 15,000 liters a year. So what does that mean for lithium? Well, adding it all together, the lithium output from the Marcellus could be substantial. It's somewhere between approximately 1,200 metric tons on the higher end of our estimates a year. And that's a very conservative estimate. So that's really focusing on, this is just water that's already at the surface that's being transported around and reinjected. So like last year, if we were to just, all of the produced water that all of the operators and you fantastic GIS people have modeled through pipeline infrastructure and things like that, and trucking routes and stuff, this is like the lithium that we could have pulled from that. And that equates to somewhere between 30 and 40% of our import reliance right now. Could just come from Marcellus produced water in Pennsylvania. So that's significant. But more interesting is, if you want to develop infrastructure and you want to have some sort of forward-looking or forecast, like, well, what does this mean for my operation footprint? What does this mean for where I have wells, the regional analysis? We found that the southwest part of the state can make about a ton of extra lithium per well compared to let me back that up. The typical Marcellus well in the southwestern part of the state makes about, on average, 1 ton more lithium per life cycle or per EUR than a well in the Northeast. And that was kind of shocking because you would think because the higher grade ore is in the Northeast, but it's not really driven by concentration, it's driven by the volume of water that you're producing. And so, at 127 milligrams per liter in the Southwest, it's still, significant enough that just that it's making twice the amount of water means that it's going to make more lithium. And there were some other metrics we looked at. So there are several different ways that you can extract lithium. The Marcellus is it's a fairly complex brine compared to some of the other produced waters that we've looked at. And so one metric that can reduce that influences the efficiency of extraction and the particular type of pretreatment and things like that you'd have to do is the magnesium to lithium ratio of the waters. And these are actually both relatively low. Seawater is somewhere between 2 and 3 orders of magnitude. And so across the board, like the Northeast and Southwest part, like Marcellus water has a low magnesium to lithium ratio. However, the Northeast part of the state, where we have the higher lithium concentrations, lower production, has a really low one. It's what are we looking at? It's like 5. Median is 5. And to give you an example of the Atacama Desert, the brines we're producing out of there, which are like the highest grade lithium brines in the world currently, are somewhere between 4 and 9. So again, this really holds up as potentially having a lot of potential to be both, I can't say economics until we run the numbers, but there's just a lot of lithium to be had here. And so if we maybe invest in this, it could have a return. But this is just a summary of, we have a lot of lithium in the Marcellus. It could make up a significant portion of our import reliance. The lithium ultimate recovery between wells in the Northeast and Southwest parts of the state is, it is different. The Southwest can potentially make more lithium over an extended period of time relative to the Northeast. It's important to note that the center of the state, so Armstrong, Clearfield, those middle counties are still relatively uncharacterized, and we have like the highest values that we've strategically located in that, but we had like 30 of them, right? So we couldn't really do a full meta-analysis like we do where we have these large well populations in regional parts in the Northeast and Southwest. So again, this is conservative number. These are conservative estimates. Most of the lithium that you're going to produce is produced within the first 2 years or so. So there's an 80% decline in production over the first 2 years of the well. And with that, I'd like to thank the Department of Energy. This work was funded through the Minerals Sustainability Research Program. And then also, I'd like to especially thank Range Resources for helping us with our data gaps and facilitating industry discussions to see if this was even a realistic idea or not. So with that, thank you.